All right, guys, I wanted to explain these example problems that are on the PowerPoint. Our first question asks us to find the mass of sodium chromate needed to precipitate all the silver ions out of a solution of 75 milliliters and a 0.1 molar silver nitrate solution. So what you have to start with are the things you know, which is the 75 milliliters and the 0.1 molar. You can do that algebraically, but I do find it easier just to use T-charts. So the 75 milliliters does need to be in liters to use molarity, which is moles per liter. So I have moved the decimal place over and get 0.075 liters of the silver nitrate. Now I want to cancel out my liters and go to the 0.1 moles of the silver nitrate shown here. So remember, molarity is moles per liter. That means I've got 0.1 moles per 1 liter. That's where that comes from. Okay. Then I'm going to use my mole ratio to cancel out my moles of silver nitrate to moles of sodium chromate. And then sodium chromate happens to weigh 162 grams per mole. T-charted away, and I get 0.608 grams needed to precipitate that amount of silver from the silver nitrate. Okay. In the next example, instead of using a molecular equation, we're going to look at the net ionic equation. Okay. So different equations can be used differently. So here's our second example. We've got the we have the sodium phosphate solution reacting with the lead 2 nitrate solution, producing the lead 2 phosphate, and the sodium nitrate are our spectator ions. Because those are our spectator ions, the net ionic is provided here, that there would be 2 phosphates and 3 leads in lead 2 phosphate, right, crossing our charges. This question asks what volume of the lead 2 nitrate solution, what volume of the sodium phosphate solution, phosphate's over here this time, would be needed to precipitate all the lead ions from 150 milliliters of a 0.25 molar solution. So in this scenario, again, I want liters, so that's 0.15 liters in a 0.25 molar, so molar is moles per liter. That means there's 0.25 moles in a liter of that solution. They are in a 3 to 2 mole ratio, according to our balanced net ionic equation. And every 0.1 mole of that phosphate ion is in a liter. So then I can get the volume, which would be 250 milliliters needed to precipitate all those lead ions out of that solution that was given. Okay. Now the last example, or the last question, is asking us at the very end to calculate all of the concentration of each ion. For this scenario, what I found to be the most helpful is to use a complete ionic equation and a BCA table. Okay, so to start, what we can see is that I have my balanced molecular equation here at the top, that silver nitrate reacts with the calcium chloride, producing silver chloride and calcium nitrate. However, these are my spectator ions, right, which means they are not involved in the reaction and do not undergo any chemical change. Okay. I was given 0.2 molar, 100 milliliters of a 0.2 molar silver nitrate, and a 0.15 molar 100 ml solution of that calcium chloride. What I found to be more helpful than when I did this in class is that I separated all the ions into the complete ionic equation. This was helpful for me because in my BCA table I got to separate each ion out to find the concentration at the end. Okay, so using my complete ionic equation and knowing that if molarity is moles over liters, that molarity times liters is going to give me my moles, then the 0.2 times the liters here, which would be 0.1, so 0.2 times 0.1 gives me those 0.02 moles of silver ions. Being that they are in a 2 to 2 mole ratio or a 1 to 1 mole ratio, that is also the amount of moles of my nitrate ions. I was also given the 0.15 molar in 100 mils of the calcium chloride solution. So again, I don't want to use milliliters, so move my decimal place. The 0.15 molar times the 0.1 liters gives me 0.015 moles of calcium. They are not in a 1-to-1 ratio. Calcium will dissociate. For every 1 calcium, every 1 mole of calcium, I get 2 moles of the chloride. So I would need to double this concentration for my chloride ions. Okay. When I'm doing my before, because I don't have any silver chloride yet, that gets to be a 0. However, these are my spectator ions, which means they're there before, and they're there during, and they're there after. So I went ahead and wrote that these exist as well on this side of the equation. Okay, I just copied those from here over to here. All right. In the change, what I needed to decide was whether my silver or my chloride was my limiting reactant. So being that I have 0.03 moles of the chloride and only 0.02 moles, and they are in a 1-to-1, 2-to-2 mole ratio, this one's higher, so this is my excess reactant. This one's lower, so it's my limiting reactant. Therefore, when I subtract my limiting away, there is no silver left over at the end, but there is 0.01 moles of those chloride ions left over at the end. Since there's no change to my spectators, I just brought those down low. And again, those are the same numbers that are on this side. Because the silver is my limiting reactant, and it is in a 1-to-1 or 2-to-2 mole ratio, I'm going to produce 0.02 moles of silver chloride, seen here. Okay. Now I can answer all the questions given to me through my BCA table. The first question was to find the mass of the silver chloride precipitate. So just multiplying my moles that I produced times molar mass gives me that mass of precipitate. Pretty simple. The next question asked me to find the concentration of each ion that remains in the solution after the reaction has reached completion. Well, because my silver was my limiting reactant, I have no moles of that left over. Now, something to think about is that we combined a 100 ml solution with a 100 ml solution. Therefore, we are diluting our other ions. So instead of dividing by 0.1, we are now dividing by 0.2. That's the 200 milliliters of both of those solutions combined. That gives me no molar of my silver ions left. However, for my nitrate ions, I can clearly see, right, in both sides of my equation that I have 0.02 moles of those nitrate ions divided by my 200 milliliters gives me a 0.1 molar nitrate ions left in solution. My calcium is also a spectator ion, so its concentration, its moles did not change. Divide by my milliliters, or my 200 milliliters, or my 0.2 liters to get me a concentration of 0.075. And then my chloride ions, because I did need to do a subtraction there, I would use those 0.01 moles divided by my 200 milliliters, or 0.2 liters, to get my concentration of 0.05 molar. I hope this explanation is smoother than it went in class, and come with questions tomorrow.